Now next up, we have regulation by fructose 2,6-bisphosphate. Now we've already looked at glycolysis as well as gluconeogenesis, and in part how it's regulated. It's pretty logical to understand why end products such as ATP can inhibit glycolysis. But the reason why fructose 2,6-bisphosphate can activate some glycolysis enzymes may not be quite so intuitive. So how does fructose 2,6-bisphosphate fit into the glycolysis pathway? It's best to think of fructose 2,6-bisphosphate as a regulation molecule or a side process that can go along with glycolysis or gluconeogenesis. Now fructose 2,6-bisphosphate is formed by phosphofructokinase 2 when fructose 6-phosphate gets converted to fructose 2,6-bisphosphate. And the reverse reaction can also take place, where fructose 2,6-bisphosphate is acted on by fructose bisphosphatase 2 to form fructose 6-phosphate. An important point to remember here is that fructose bisphosphatase 2 as well as phosphofructokinase 2 are actually a part of the same protein, but they respond in opposite ways to phosphorylation by protein kinase A. Alright, now let's compare the regulation of this enzyme in the fed as well as the fasting state. Now in the fasting state, high glucagon increases the amount of cyclic AMP through a G protein coupled receptor. This increases the activity of protein kinase A, which phosphorylates fructose bisphosphatase 2. This phosphate group activates fructose bisphosphatase 2 and inhibits phosphofructokinase 2. This means that you're going to be converting the side molecule of fructose 2,6-bisphosphate into fructose 6-phosphate and inhibiting the opposite reaction. Now this in turn allows gluconeogenesis to proceed and replenish blood glucose levels, which makes sense since you are in the fasting state. So with all that being said, what do you think would happen in the fed state? Well, in the fed state, high insulin levels decrease the amount of cyclic AMP and therefore decrease protein kinase A activity. With decreased protein kinase A activity, the enzyme fructose bisphosphatase 2 will end up being dephosphorylated, which means that only phosphofructokinase will be active. The body will then start converting fructose 6-phosphate into fructose 2,6-bisphosphate, which in turn activates phosphofructokinase 1, as you can see here. Now, with phosphofructokinase 1 being active, this allows glycolysis to proceed, and it does this by converting fructose 6-phosphate into fructose 1,6-bisphosphate, which then enters the glycolysis pathway. Now, it's important to remember that the molecule fructose 2,6-bisphosphate is made to regulate the steps of glycolysis. And also keep in mind that phosphofructokinase 1 is the rate-limiting step in glycolysis. So it's important to regulate this enzyme more than the other enzymes. And while we're on it, can you name a few other phosphofructokinase 1 regulators? Great, that'd be ATP and citrate, which inhibit phosphofructokinase 1, and AMP and fructose 2,6-bisphosphate, which stimulate phosphofructokinase 1. Alright, now let's take a shot at a flash quiz. A hard-working medical student is on her surgery clerkship and skips lunch to go to the OR. How does this affect the action of fructose bisphosphatase 2 and phosphofructokinase 2? There you go. It's going to activate fructose bisphosphatase 2 and inhibit phosphofructokinase 2. Just remember, in the fasting state, you get increased glucagon levels, which increase cyclic AMP, and this leads to activation of protein kinase A, which phosphorylates fructose bisphosphatase 2, ultimately activating it. This will again go on to limit glycolysis, as well as increase gluconeogenesis to restore blood sugar homeostasis. Alright, well that'll wrap up regulation by fructose 2,6-bisphosphate. See you in the next video.